National Electrical Code, or NEC, does not explicitly require a source to provide enough fault current to open its output breaker. However, the NEC does state that overcurrent protective devices must be rated to interrupt the fault current that can flow in the circuit, as per NEC 110.10. IEEE STD 1500-2018, IEEE Guide for Arc Flash Hazard Analysis of Power Systems, recommends that sources provide sufficient fault current to open the protective device within the relay settings, for example, 0.1 seconds. There may be local or industry-specific codes or standards that address this issue. However, it is unlikely that these would explicitly require a source to deliver enough fault current to open its output breaker. Based on the information, it is unlikely that there is a code violation in this case, since the NEC does not explicitly require sources to provide enough fault current to open their output breakers. However, it is recommended to refer to specific local or industry codes and standards for further clarification. While not required by code, providing sufficient fault current to open the output breaker is generally a good safety practice. This ensures that the breaker can effectively clear fault, preventing potential damage and injury. Consider replacing the 100 amp breaker with an 80 amp breaker to ensure that the UPS can clear the breaker if a fault occurs. Adding a separate instantaneous trip device to the UPS output to provide backup protection in case the breaker fails to open quickly enough is a good idea. Regularly testing the UPS and the output breaker to ensure proper operation is critical. The key consideration is ensuring the overcurrent protection device, such as the breaker, is properly rated to interrupt the available fault current. The NEC section 110.9 addresses interrupting rating. Equipment intended to interrupt current at fault level shall have an interrupting rating sufficient for the nominal circuit voltage and the current that is available at the line terminals of the equipment. Equipment shall be marked with its interrupting rating. This means that any electrical equipment that is designed to interrupt fault currents needs to be rated to handle the amount of fault current that could potentially flow through it. This interrupting rating needs to be clearly marked on the equipment. If equipment is installed in a location where the available fault current exceeds its interrupting rating, then the equipment needs to be protected by another overcurrent protective device. This protecting device needs to have an interrupting rating that is equal to or greater than the available fault current. The available fault current is the maximum amount of current that could flow in a circuit under fault conditions. It depends on factors such as the voltage of the source, the impedance of the circuit, and the size of the conductors. The interrupting rating of a piece of equipment is the maximum amount of current that the equipment can safely interrupt without being damaged. The NEC also states in 110.10 regarding circuit impedance, fault current, and interrupting rating that the overcurrent protective devices, the total impedance, component short circuit current ratings, and other characteristics of the circuit to be protected shall be selected and coordinated to permit the circuit protective devices used to clear fault to do so without extensive damage to the electrical equipment. This means that when a fault happens, the protective devices in the circuit should be able to quickly and safely cut off the current flow without causing significant damage to any of the electrical components in the system. In other words, the circuit needs to be designed in such a way that the protective devices can effectively do their job of clearing faults without causing more problems. This involves carefully selecting the right protective devices, considering the impedance of the circuit, making sure the components can handle short-circuit currents, and coordinating everything so that the protective devices work together properly to clear faults safely. In the case of a UPS system, the available fault current is limited by the UPS design. If the output breaker is rated higher than the maximum fault current the UPS can deliver, it raises concerns. Firstly, the breaker might not trip quickly enough under fault condition. Overcurrent protective devices like circuit breakers are designed to trip within a specific time frame when the current exceeds their rating. If the fault current is significantly lower than the breaker's rating, the tripping time might be delayed. This delay could lead to increased damage to equipment and conductors due to the prolonged fault current. Secondly, the breaker might not trip at all. If the fault current is below the breaker's minimum tripping threshold, the breaker might not trip at all. This situation is extremely dangerous because the fault will persist indefinitely, leading to severe damage and potential fire hazards. Thirdly, coordination issues can arise. Electrical systems are often designed with multiple overcurrent protective devices coordinated to isolate faults effectively. If the UPS output breaker is oversized, it can disrupt this coordination, potentially causing upstream breakers to trip unnecessarily, leading to wider power outages. Several options can be considered to address this situation. Firstly, reducing the breaker size is a good approach. Replace the 100 amp breaker with an 80 amp breaker, matching the UPS maximum output current capability. This ensures that the breaker will trip quickly and reliably under fault conditions. Secondly, using a current limiting breaker is an option. Install a current limiting breaker that can rapidly reduce the fault current to a safe level. This type of breaker can provide faster and more effective fault protection. Thirdly, adding supplemental protection can improve safety. Implement additional protection devices such as fuses or ground fault circuit interrupters, or GFCIs, to provide backup protection in case the main breaker fails to operate correctly. Fourthly, reviewing the system coordination is important. Conduct a thorough review of the entire electrical system to ensure that all overcurrent protective devices are properly coordinated to minimize the impact of faults. Several factors can limit the fault current from a UPS. Firstly, impedance is a factor. The internal impedance of the UPS limits the amount of fault current it can deliver. Secondly, the inverter design is critical. The design of the UPS inverter also plays a role in limiting fault current. Thirdly, current limiting circuitry protects the UPS. Many UPS systems incorporate current limiting circuitry to protect themselves from damage during fault conditions. When assessing a UPS installation, several checks should be performed. Firstly, determine the available fault current. Calculate or measure the available fault current at the UPS output. Secondly, verify breaker ratings. Ensure that the breaker is rated appropriately for the available fault current. Thirdly, check the coordination. Verify that the breaker is coordinated with other overcurrent protective devices in the system. Fourthly, perform regular testing. Implement a regular testing program to ensure that the UPS and its associated protection devices are functioning correctly. Considering the potential safety implications of inadequate fault current protection, it's always best to err on the side of caution. Consulting with a qualified electrical engineer is crucial. An engineer can perform a detailed analysis of the electrical system and provide specific recommendations for ensuring adequate fault current protection. Several additional points should be kept in mind when evaluating UPS installations. Firstly, documentation is critical. Maintain accurate documentation of all electrical equipment, including breaker ratings, cable sizes, and system diagrams. Secondly, training is essential. Provide training to personnel on proper electrical safety procedures and the operation of UPS systems. Thirdly, stay updated with codes and standards. Keep abreast of changes to relevant electrical codes and standards. The determination of available fault current requires calculations involving transformer impedance, conductor impedance, and other components in the circuit. This calculation can be complex, and it's often best to use specialized software or consult with an electrical engineer. Several types of breakers are used in electrical systems, each with its own characteristics and applications. Firstly, standard thermal magnetic breakers are the most common type of breaker. They use a thermal element to trip on overload currents and a magnetic element to trip on short-circuit currents. Secondly, instantaneous trip breakers trip very quickly on short-circuit currents. They are often used to protect sensitive equipment. Thirdly, current limiting breakers reduce the magnitude of fault currents. They can help to protect downstream equipment from damage. Several standards and guidelines provide guidance on fault current protection. Firstly, the NEC, or National Electrical Code, provides requirements for the installation of electrical equipment, including overcurrent protection. Secondly, the IEEE, or Institute of Electrical and Electronics Engineers, provides standards and guidelines for the design and operation of electrical systems. Thirdly, NETA, or International Electrical Testing Association, provides standards for the testing and maintenance of electrical equipment. It is also important to be aware of arc flash hazards. Arc flash is a dangerous electrical phenomenon that can occur during a fault. Arc flash can cause severe burns, blindness, and even death. Proper fault current protection can help to reduce the risk of arc flash. Regarding the NEC, there are several relevant sections to consider. NEC 110.9 covers interrupting rating and requires equipment intended to interrupt current at fault levels to have an interrupting rating sufficient for the nominal circuit voltage and a current that is available at the line terminals of the equipment. NEC 110.10 discusses circuit impedance, fault current, and interrupting rating, stating that the overcurrent protective devices, the total impedance, component short circuit current ratings, and other characteristics of the circuit to be protected shall be selected and coordinated to permit the circuit protective devices used to clear a fault to do so without extensive damage to the electrical equipment. NEC 240.2 defines overcurrent as any current in excess of the rated current of equipment or the ampacity of a conductor. It may result from overload, short circuit, or ground fault. NEC 240.1 provides the scope, and this article covers overcurrent protection and coordination requirements designed to provide protection for equipment, systems, and people. It's important to remember that electrical codes and standards are constantly evolving. It is important to stay up to date on the latest requirements. The role of an electrical engineer is critical in ensuring safety. Electrical engineers play a vital role in designing, installing, and maintaining electrical systems. They have the knowledge and experience to ensure that these systems are safe and reliable. When working on electrical systems, it's important to follow all safety precautions. Always to energize equipment before working on it. Use appropriate personal protective equipment, or PPE, such as gloves and eye protection. Be aware of potential hazards, such as arc flash. Regular inspections and maintenance are critical. Electrical systems should be inspected and maintained regularly to ensure that they are operating safely and reliably. Breakers should be tested periodically to verify their functionality. Wiring should be checked for damage or deterioration. The system should be kept clean and free of debris. Ultimately, the goal is to create a safe electrical system. By following these recommendations, it is possible to create an electrical system that is safe for personnel and protects equipment from damage. In summary, while the NEC does not explicitly mandate that a UPS system must be able to deliver sufficient fault current to open its output breaker, adherence to best practices, consideration of safety, and compliance with relevant standards are crucial. The key is to ensure that the overcurrent protection devices are properly sized and coordinated to protect the electrical system and personnel from the hazards of fault currents. It's recommended to consult with a qualified electrical engineer to perform a comprehensive assessment and provide tailored recommendations for the specific UPS installation. Regularly scheduled maintenance and testing is equally important to ensure the longevity and proper operation of the electrical equipment. Consider these factors for a comprehensive and safe electrical installation.